In this video, we're going to be talking about polar form of complex numbers. So I wanted to give you at least one application of polar coordinates before we just ended the semester and just said, well, why the heck did we even talk about that? Besides my allusion to you will use polar coordinates in second semester calculus. That's not a very good answer. So let's talk a little bit about how we can do polar form of a complex number. So before we get to the polar form, let's just talk a little bit about how we can represent a complex number graphically. So, for our purposes here, let's look at this first one here where we got 1 plus 3i. Well, if you remember from your discussion of complex numbers before in college algebra, this part is called the real part, and this part is called the imaginary part. And that's how we write the numbers as a plus bi. So, and then remember that I is your square root of -1. So basically it gives you a way to solve equations like x squared equals -1 that you weren't able to solve for before you introduced complex numbers. We're not going to be doing much, well, we're not going to do any solving that has to do with complex numbers. I literally just want to be able to write these things in complex form, or if it's in complex form, change it back to rectangular form. All right, but again, I want to just represent these things graphically. Okay, so if I have a real part and an imaginary part, I can think of this almost as an ordered pair, a 1 kind of a 3. Because we know that the 1 goes with the real part, the non-I part, if you will, and the 3 goes with the I part, the imaginary part. So thinking of it as an ordered pair, it makes sense now to plot it. I go over to the right 1 and up 3. So this is your 1 plus 3i represented graphically. Not too bad. You use the real part for your x, which is why we've got it labeled as the real axis here. And you use the imaginary part for the y, which is why I have the imaginary axis here. If you just remember to treat the real part as x, imaginary part as y, plotting these things is not that big of a deal. So here, if I've got 2 minus 2i, the real part is 2, so I would go right 2. And the imaginary part is -2, so I would go down and get the point to -2. So that would be your 2 minus 2i. Same idea here. I have a -2, so I would go left -2. And then I have 2 root 3. Root 3 is about 1.7, so 2 times that's about 3.4, a little bit bigger. So we'll go up to about 3.4 and plot that there. Okay, not too big of a deal. All right, last one here. I just have -4i. Well, the real part is 0. I can imagine this is a 0 minus 4i. So I don't go left or right at all. I stay on the imaginary axis, and then I go down to -4. So this would be where we would plot that point. All right. So the next part asks us to find the absolute value, which also is known as the modulus, which is also known as the magnitude of each of these complex numbers. That is a lot of words for something that's not very difficult because it's the same kind of thing we've just been doing back in the polar coordinates leading up to this section. Let me draw a different color here. When we want the absolute value, all it's asking for is that distance from the origin. Literally, that's all it's asking for. So the length of this segment is the absolute value of the complex number. And let me write that word a little bit better because that was an ugly V. All right. Okay, so if we want, and we actually use the absolute value, 1 plus 3i. Well, the distance then is not too bad to figure out because I go right 1 and up 3. So that's a Pythagorean theorem idea. We'll do square root of 1 squared plus 3 squared. That looks like that r back in the polar coordinates, right? Was we had r squared equals x squared plus y squared. So to find r, you would take the square root. Same exact idea here, which is not a huge surprise if we're going to polar form of complex numbers, by the way. So we get square root of 10 here. absolute value of the 2 minus 2i, we would do square root of 2 squared plus 2 squared. That's square root of 8, which I can simplify to 2 square root of 2. This will always be a real number, by the way. You will not get i's in your absolute values, okay? Because notice all we're doing is peeling. We're not even dealing with the I, right? We're just taking the different components and squaring them. So you're never going to get an I out of this. This is always going to be a real number. If I want to do absolute value of negative 2 plus 2i root 3, that's square root of negative 2 squared. And the piece that's multiplied by the I, the whole thing, is 2 root 3 squared. 2 squared is 4. 2 squared is 4 times root 3 squared is 3. So that's times 12. That gives us square root of 16, which is 4. And finally, the last one. This one, you don't even necessarily have to plug into the formula. You can just count units, right? This is 4 units below the x-axis, or 1, 2, 3, 4 away from the origin. So I can just get 4. But if you like to use the formula, 0 squared plus negative 4 squared, it definitely gives me 4. So that's the modulus, the absolute value of complex number. All right, so let's go to polar form then. You might have already guessed what that polar form might be. All right, we've already talked about how we have an x and a y if we want to plot x plus y times I, right? We go x units in the real direction and y units in the imaginary direction. But we've already talked about, with polar coordinates, how to get an r and a theta. Right? We know that our x is r cosine theta, and our y is r sine theta. So when we do the polar form of the complex number, the polar form will be r cosine theta plus, I'll write it this way, r sine theta times I. Now notice that we can factor an r out of both of those terms. And I have cosine theta, and usually we put the I in front of the sine. So we write it as r cosine theta, or r times cosine theta plus I sine theta. Let me make a little better box around that so I don't cross through the r. So that's how we find the polar form of the complex number. If we know x and y, we do our conversions to get r and theta and then put it into that form. All right, so let's see if we can do a couple of examples here. So these problems ask us to convert from rectangular to polar or from polar to rectangular, depending on the form of the problem. All right, so this one, these first 4 are all in rectangular form. So this is my x, this is my y, right? So I can figure out what r is. R squared is x squared plus y squared. The x is negative 2 root 3, and the y is negative 2. This gives me 4 times 3 gives me 12, plus 4, I get 16. So that tells me my r has to be 4. Notice again that this is the absolute value of the number. So the r is the absolute value. The absolute value of a complex number here gives you the distance from the origin. Okay. Now we need to find theta. We remember that tangent of theta is y over x. Y in this case is negative 2, and x is negative 2 root 3. So we get tangent of theta is equal to 1 over root 3. Well, we know that one angle that gives us a tangent of 1 over root 3 is pi over 6. However, we have to go, remember when we were doing conversions for polar coordinates, we have to go back and check where this would be if we think about plotting it. Okay? Well, if I plot this complex number where this is the real axis, so I'm using that funky looking R for the reals, and this is the imaginary axis, denoting it with an I, then I would go negative 2 root 3 and negative 2. I would be down here. This is quadrant 3, right? So I don't want pi over 6. I want the pi over 6 angle that's over in quadrant 3, and that's 7 pi over 6. All right, so we found the R, we found the theta. So the last thing here that we need to do is we need to write this in polar form. So to write this in polar form, then the last step here will be, remember let's go back up to the top, go back up to the formula real quick here. So back up here, the formula says that we write the R out in front and then do cosine of the angle plus I sine of the angle. And literally, we want the cosine and the sine in the answer. Okay. So when I go back down here, when I write the answer, we'll write it off to the side because I don't have a lot of room here. We will write it as 4 times cosine of 7 pi over 6 plus I sine of 7 pi over 6. And this is the answer. No simplifying. This is the answer. That's the polar form of the complex number. Okay. So let's do a few more of these. Again, this is my x, this is my y. R squared equals x squared plus y squared. X is square root of 21. Y is square root of 7. It's not too hard to see that this is 28. So R is going to be square root of 28, and I can simplify that to 2 square root of 7. All right, so now let's figure out what theta is. We know that tangent of theta is y over x. Y is square root of 7. X is square root of 21. This may not look like you can do the exact value, but it's rigged so in this particular case so that you can. 21 is 3 times 7. So this simplifies to tangent of theta equals 1 over root 3 again. So our theta must be pi over 6, or some multiple of pi over 6 I have to go find. So remember, again, we need to go back and look at the number. The number here is a positive x, it's a positive y. That means if I plot the complex number, it'll be in quadrant 1, and pi over 6 is the correct angle then in that case. So your polar form is going to be 2 square root of 7 times cosine of pi over 6 plus I times sine of pi over 6. Again, no simplifying. We just put the r in and the cosine into that form for the polar form, and that's it. Okay, so let's look at these next two. Looks a little ugly, but it's not so bad. Okay. All right, so here again we have r squared is equal to x squared plus y squared. The x is negative 5 square root of 2 over 2, and we square it. And so is the y. Okay, so what do we get? We square the 5, we get 25. We square the root 2, we get 2. So we get a 50 on top and a 4 on bottom. So that gives me 25 over 2 for both of these, which adds up to, that was weird, which adds up to 25. So that tells me the r has to be 5. Like I said, they look ugly, but that particular simplifying wasn't so bad. All right, now let's find our theta. Tangent of theta is y over x. Rather than writing all these numbers in here, notice that your y and your x are the same number. So we get tangent of theta is 1. Those will cancel each other out when you put it on top and bottom. I'm being lazy here. I don't feel like writing it down. Right? The y and the x are the exact same number. Well, the angle that has a tangent of 1 is pi over 4. or some multiple of pi over 4. So again, we need to look back at the number. X is negative and y is negative. This means that this number is in quadrant 3. So I have to use 5 pi over 4 for this one. That's the pi over 4 angle over in quadrant 3. So then finally, when we do the polar form, it'll be 5 times cosine of 5 pi over 4 plus I times sine of 5 pi over 4. And that's it. All right, let's do this last one. 2I. Well, let's do this one a little bit easier way, rather than going through all the r's and the thetas. I think this was just as easy to see what's going on. Here's a 1, oops, negative 1. This would be 1, 2, 1, negative 1, whatever. All right, when I plot this point, notice it's 0 plus 2I. That means I would just go up here and plot the point 0, 2. And I want the polar form for that 0, 2. Well, it's pretty easy to see then that that point is 2 units away from the origin, right? It's 2 units away from the pole because I just went up 1, 2. That's 2 units. It's also easy to see, hopefully, that the theta has to be pi over 2 because that's the angle this way, right? That is pi over 2 going that direction. So then our polar form is 2 times cosine of pi over 2 plus I sine of pi over 2. If you can convert rectangular coordinates to polar coordinates, then you can convert rectangular forms of complex numbers to polar forms of complex numbers. And it's even easier to go the other way. Okay? So notice that the ones here at the bottom, these last 4, are already in polar form, right? So these must be going from polar to rectangular. But again, if we have this in polar form, going to rectangular is easier because all we have to do is simplify. Literally, we just have to, in this case, we want to compute the values and simplify. So for this one, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we get 0 plus I times 1. And if I simplify, if I distribute the square root of 6, square root of 6 times 0 is 0, I just get I square root of 6. It's possible when you enter a number in Hawks sometimes, a lot of times likes it where the I is behind it. So you may, if you put this in Hawks, this is Hawks only, by the way. I don't care if you do this. It may want you to put the square root of 6 and then put the I. But this is a very, very be careful moment. Don't put the I under the square root. I want that square root of 6 by itself and then the I put behind it. But again, this is a Hawks thing. It likes A plus BI. It likes the I on the end a lot of times when you put in answers. So be aware of that. If you put it as I root 6, it's going to tell you to re-enter it. And that's probably what it wants you to do. Okay, now let's do this one. Same idea though. All going from polar to rectangular is just simplifying. Cosine of 4 pi over 3. Well, 4 pi over 3 is in quadrant 3. So the cosine will be negative, and it's a pi over 3 angle, so that's negative a half. 4 pi over 3 again is in quadrant 3, so sine will be negative, and it's a pi over 3 angle, so it'll be negative root 3 over 2. And now I just need to distribute. 2 times 1/2 is 1, so I get a negative 1. 2 times negative root 3 over 2 gives me a minus I root 3. And again, if you're doing Hawks, it's probably going to want negative 1 minus root 3 I. And again, make sure that that I is not under your square root. That would actually be wrong if you put this I under the square root. Which is another reason why most people put the I in front of it. The I doesn't belong under the square root. And if you write it behind it and you're sloppy, you can't really tell if your square root bar goes over the top of it or not. In every single problem that you're going to do, the I does not belong under the square root. Okay, so you're never going to have to worry about it. It's for you, it's always going to be outside of the square root, without a doubt. All right, last two. Seven pi over 4 is in quadrant 4. So cosine is positive. It's a pi over 4 angle. So that's 1 over root 2. 7 pi over 4 is in quadrant 4, we just said. Makes sine negative. And again, it's a pi over 4 angle, so that makes that 1 over root 2. So if you're distributing this, it would be 8 over square root of 2 plus, minus I times, or actually I would probably write it as 8I over the square root of 2. Another thing Hawks probably wants you to do in this particular instance would be rationalize your denominator. So if I multiply top and bottom by square root of 2, you would just get 4 root 2 and then minus 4I root 2 here. And then again, if you're doing Hawks, you'll probably want to put that I on the end. Honestly, on your exam, if you write this, I'm going to be happy as a clam. I don't care about the rest of the arithmetic simplifying. Okay, very last one. 5 pi over 6 is in quadrant 2. It's a pi over 6 angle, negative root 3 over 2. Again, quadrant 2, sine is positive. It's a root 3 over 2 angle, so it's a 1/2. And then distribute your 4. 2 goes into the 4 twice, so you get negative 2 root 3, and then 2I. So this would be your final answer in this case. And that's it. That is going back and forth between rectangular and polar form for complex numbers. And this is literally all I want you to be able to do as far as the complex number stuff goes. So this is the last section that we're going to cover this semester. Thank you all for being patient and dealing with all of this craziness due to the fact that we had to go online because of the pandemic stuff. And I really do appreciate you working hard and doing stuff and being amenable to having live meetings and then not having live meetings with my internet being crazy. And I just want to know that I really do appreciate it. Nobody signed up for any of this, so the fact that you were able to get through it and do this, I couldn't be happier as far as that goes. So anyway, again, like usual, if you've got questions, feel free to ask them. I will post some extra practice problems for these on Moodle as well, so you have practice problems and solutions to go along with these. And then your exam will be live here on Monday so that you can turn it in on a Wednesday. So anyway, have a good one. And again, if you've got questions, give me a holler.